Welcome to this course on modern C++ design patterns. And in these videos, I'll be talking about what design patterns and idioms are and showing you how to implement some typical examples in C++. The course is designed for beginning to intermediate C++ programmers who want to improve their design and coding skills. I'm assuming that you have at least 6 months' experience of coding in C++, have a good understanding of object-oriented programming, and are familiar with the basic use of templates. And of course, it goes without saying that you have a desire to learn more. The course introduces the concepts of design patterns and idioms, and then goes on to show how some have been traditionally implemented in C++. Two developments have changed the way in which C++ developers write code. The releases of C++ 11 and 14 have added many important new features to the language, and there is now an increasing awareness that functional programming techniques can help write more robust and maintainable code. So we'll look at these, and then in the final chapter, see how we can use them to write up-to-date implementations of several patterns and idioms. So by the end of the course, you'll have an appreciation of what design patterns and idioms are. You'll also know about the additions made to C++ by the C++ 11 and 14 releases, appreciate the advantages of functional programming, and see how these can be used to implement patterns and idioms. Design patterns and idioms are important concepts, helping programmers to produce good code and avoid pitfalls. So what is a design pattern? A design pattern is commonly defined as being a tested solution to a recurring problem in a particular context. So let's take this apart and see what it implies. To qualify as a design pattern, a solution has to be tested and its pros and cons well understood. Design patterns document solutions that have been discovered and refined over time by experienced programmers. It always seems a little strange to see design patterns described for technologies that are only a few months old and so can't have been tested that much. Secondly, the problems solved by a pattern should be widely applicable. It isn't really worth taking the trouble to document the solution to a problem if it isn't likely to recur or if no one else is going to encounter it. All design patterns have a context and may not be applicable or may even be actively harmful if used outside that context. For example, a pattern used to solve problems with web applications may well not be suitable for real-time applications. And finally, patterns are designed to present best practices in a practical way, building on the knowledge of experienced developers. There's a saying that patterns are discovered, not invented. If something really is a best practice, you'd expect experienced practitioners to discover it independently because it is the best way to do the job. In fact, since patterns are best practices, you may well have discovered some for yourself, and it is quite common for a good developer to get a slight feeling of anticlimax when hearing about patterns. Why? Doesn't everyone do it like that? Design patterns have several advantages for the developer. First, they provide a shared language that improves communication, making it easier to communicate insight and experience about problems and how they can be solved. For instance, when someone says they used a visitor, it's a concise way of saying that they want to add functionality to a class without changing it, separating the operation from the class being operated on. And, of course, using design patterns helps you build on the experience of others. Not only does this help you to avoid problems and pitfalls that may not be obvious, but it also guards against reinventing the wheel, thinking up your own solution to a problem where a perfectly good one already exists. A good programmer is humble, recognizing that he or she doesn't necessarily know everything and that a homegrown solution is unlikely to match established best practice. Where did design patterns originate? An architect called Christopher Alexander discovered patterns in architectural designs, and he published a book called A Pattern Language: Towns, Buildings, Construction in the 1970s. This defined 253 patterns that formed what he called a pattern language. Kent Beck and Ward Cunningham began studying patterns in software in the early 1980s, and Erich Gamma became interested in them while doing his PhD. Gamma and Richard Helm began cataloguing patterns in 1991. They were then joined by Ralph Johnson and John Vlasides, and they all became known as the Gang of Four. Their work was published as a book, Design Patterns: Elements of Reusable Object-Oriented Software. This is now universally known as the Gang of Four book and describes 23 basic patterns. I don't think it is an exaggeration to say that this book kick-started the whole design patterns industry. So what were the original patterns? The 23 patterns described by the Gang of Four book can be divided into 3 groups by function: creational, structural, and behavioral. Creational patterns describe ways of creating objects. Structural patterns deal with how objects are built into larger structures, and behavioral patterns relate to runtime behavior. They can further be divided into 2 families, consisting of those that are class-based and those that are object-based. And here we can see the 23 patterns divided into their groups: factory method, which is creational and class-based; class adapter, structural and class-based; interpreter; and template method, which are behavioral and class-based. Then we have abstract, factory, builder, prototype, and singleton, which are creational and object-based; adapter, bridge, composite, decorator, facade, flyweight, and proxy, which are structural patterns but object-based; and then the rest: chain of responsibility, command, iterator, mediator, memento, observer, state and strategy, and visitor, which are behavioral object-based patterns. So let's briefly review some common patterns. Our first one is Model View Controller, better known as MVC. This was perhaps the original design pattern. It was discovered by Trygve Reenskog when he was a visiting scientist in the Smalltalk group at Xerox's Palo Alto Research Lab, and he published the first paper on it in 1978. The idea behind MVC is to decouple a model, which Reenskog originally described as knowledge, from the way in which it is viewed. Controllers provide an interface between the user and the rest of the system. MVC was discovered at the very birth of graphical user interfaces and is now the basis for countless applications and frameworks in both the desktop and web worlds. There are many variations on MVC, such as Model View Presenter and Model View View Model, all of which build on the basic idea of separating a model from its representation. So a model holds and manipulates data, which is displayed by one or more views. Controllers pass interaction information to the model, and a user interacts with controllers and views. The state pattern is used when an object needs to change its behavior when its state changes. The classic example for this might be a bank account whose behavior changes depending on whether its state is in credit or overdrawn. Object states are represented by classes, and this removes the need for multiple if and switch statements to check the state. An object known as a context refers to 2 or more state objects which implement a common interface. It's interesting to note that state is related to strategy. Both of them have the same UML class diagram, which can be thought of as a general bridge design, the difference between them being in their intent. Despite appearing simple, Singleton can be tricky to handle. We all know that it is designed to allow creation of only one instance of a class and to provide a global point of access to it, but that rather depends on your definition of one. Do you mean one instance per app, one per machine, or one in the entire world? And do you mean one physical object or one set of state so that you could have multiple instances that look identical? It's also rather harder to implement than you might think in C++, due to lifetime issues and also initialization. I'll have more to say about this later on. And finally, observer, which is designed to let a component provide notification of state changes to interested parties. Observer is a good example of a pattern that has been incorporated into many libraries and frameworks so that it is often not necessary for developers to implement it themselves. So we have an object that may change state. An observer can register a callback with the object, and when a state change occurs, the object sends notifications to each callback in its list. As well as design patterns, we have idioms. So what is an idiom? Idioms differ from patterns in that they are specific to a language or platform. As such, idioms are rather lower level than patterns and tend to apply at the code level. Good examples of these would include pointers and templates in C++, perhaps especially templates, since there is nothing quite like them in any other language that I have come across. In languages that use garbage collection, such as Java, you will see finally used with try blocks as a way to introduce deterministic cleanup while avoiding code duplication. C++, of course, doesn't need this because destructors give us real control over object lifetimes. Functional languages, including Haskell, OCaml, and Scala, make heavy use of a feature called pattern matching, which isn't found in mainstream OO languages. So let's look at a few C++ idioms. I'll present an overview here, and then we'll cover them in more detail a little later in the course. RAII, or Resource Acquisition is Initialization, is a very common C++ idiom that relies on destructors and is the reason why we don't need finally when handling exceptions in C++. To put it simply, you can do something in a constructor and then undo it in a destructor. It is used to bind the lifetime of a resource to the life of the object using it. RAII guarantees that a resource will be available to any function that needs it, but that it won't live on beyond the lifetime of its controlling object. It also guarantees that if resource acquisition fails for any reason, all resources acquired by fully constructed members will be released, thus preventing resource leaks. PIMPL, or Pointer to Implementation, is an idiom that helps minimize dependencies on class implementation. In C++, private data members of a class are a part of its object representation, so they affect size and layout. And private member functions also take part in overload resolution. This means that any changes to private members will require recompilation by all users of that class. Moving implementation details out into another class can break the compile time dependency on implementation. And from this, it follows that two common uses of PIMPL are to provide a stable application binary interface to classes and to improve compilation times. So here we have a class that has a pointer to an implementation, meaning that users of foo don't rely on the implementing class. Smart pointers, which in C++ means overloading the arrow or crow's foot operator, are an idiom that is fundamental to modern C++ programming. And this is only possible in a language that supports both pointers and operator overloading. Overloading this operator opens the door to many useful techniques, including resource management, creating proxies of various sorts, and many more. Here we have a class called pointer_t, which overloads the arrow operator to give access to a pointer that it holds internally. And finally, we have CRTP, the curiously recurring template pattern. This was recognized in some of the earliest template code by Jim Coplian in the mid-90s. There are several uses for CRTP, but perhaps the most common is to provide static polymorphism, in which a base class is specialized on a derived class, allowing polymorphic use of derived class members without needing virtual functions. This is useful in high-performance code because virtual functions need extra indirection and an extra pointer per object, and in addition, virtual functions can't usually be inlined. So here we see a templated class B and a derived class D, which derives from it. Note how the base class has the derived class as a template parameter. Finally, a word about implementing patterns. It's important to understand that there is no one correct way to implement a pattern. Many people seem to get hung up on the UML diagrams that they see in books or on the web and think that they show the one true way to implement a design pattern. In truth, the intent is far more important than the actual structure. If that part of your design is expressing the intent of the pattern, then it is a valid implementation. Add to this the fact that patterns work together. Books and courses usually present patterns separately, like animals in a zoo, neatly labeled in cages. In code, just like in the real world, things aren't so simple, and you'll find patterns all mixed up together with a class sometimes taking part in 2 or 3 different patterns. You may see the word reification used when discussing patterns. Reification means to make something real or concrete, and in the context of design patterns, it means producing something that expresses the intent of the pattern, whether or not it exactly matches the UML. These ideas are well explained in a book by Alan Holub called Holub on Patterns, which, although not for C++ and quite old now, is very well worth a read. He discusses many design patterns and in particular shows how they interact in large-scale applications. At the end of this chapter, let me direct you to some useful reading and online resources. A lot has been written about design patterns, and I certainly can't list everything that's worth looking at, but let me pick out a few examples. Erich Gammer's original book is still worth reviewing, even though the code is not presented using modern examples or idioms. Refactoring to patterns is interesting, showing how patterns can be used when refactoring existing code. Now, if you're interested and can find a copy, Alexander's original book on pattern languages and architecture will give you a broader perspective on this whole area. And moving away from the Gang of Four, the Pattern-Oriented Software Architecture series comes in 5 volumes and covers patterns in many areas, including concurrency, resource management, and distributed computing. I'll point out 2 online resources that are worth reviewing, C2 and Hillside. The Design Patterns wiki at c2.com has been in existence for a number of years and has a lot of useful discussions about patterns and their application. The Hillside Pattern repository contains a lot of material, in particular a comprehensive catalogue of patterns. Of course, patterns are ideas and have to be realized in code in order to be useful. Let's look at how several common patterns and idioms can be implemented in C++. We're going to consider 6: RAII, state, smart pointer, PIMPL, CRTP, and Singleton. Of these 6, state and Singleton are design patterns, and the rest are idioms. I'm going to show how these common patterns and idioms can be implemented in C++ 98 before the changes made in the C++ 11 and 14 releases. We'll come to those later in the course. You'll see a lot of implementations like this in existing code bases, and a lot of books and instructional materials present them in this way. I will note that these are very simplistic implementations, designed to illustrate the principles and are not suited for real-world use. They're used to illustrate how the pattern or idiom can be implemented, and don't necessarily cater for all possible corner cases or handle errors. So let's get started. As I've already remarked, RAII, or Resource Acquisition is Initialization, essentially means doing something in the constructor of a class and undoing it in the destructor. Although it is widely used in the C++ world, as you might expect, it is also used in other OO languages that have the concept of a destructor, including Rust, D, and Ada. Locking provides a good example, so let's see how that works in practice. We know that when using a mutex, you need to remember to unlock it at the end of the protected section of code, as shown in this fragment, where we create a mutex, acquire it using lock, do some work, and then release it using unlock. But there's a danger here in that if an exception is thrown, the mutex may not be unlocked. So we can design a simple class that uses RAII to unlock the mutex after it's been used, and which will work correctly even if an exception gets thrown. So here we see the lock class, which holds a reference to a mutex. The mutex gets passed to the constructor, and in the constructor, we acquire the mutex by calling lock. The destructor releases the mutex by calling unlock. Here's how we could use it. We can create a mutex object, and when we want to use it, we create a lock object and pass it the mutex. This will lock it. We know that when the lock object goes out of scope, its destructor will be called, and this will release the mutex. But this will happen either if the try block is exited normally, or if an exception is thrown, as in this example here. So let's see what happens when we run this code. And we can see that our code starts executing. The lock object tells us that it's locking the mutex. We do work, and then an exception gets thrown. At this point, the lock object is destroyed, so we see that it is unlocking the mutex. Then, in our catch block, we see that the exception has been caught. And so, our mutex has been released without us having to remember to do it manually. Now, all the code examples that I'm going to use are available on the website for this course. I'm also using CLion to run the code, but all of this should work in any development environment that supports C++ 11 and 14. As its name implies, the state pattern is designed to represent changing object states, representing individual states by subclasses. A good sign that this pattern may be applicable is when you find similar switch statements or chains of ifs in a class's methods, all checking for the same object state. A good example might be the traditional bank account class, where deposit, withdraw, and other methods check whether the account is in credit or not. Using this pattern removes the need for these repeated checks, and code is more modular because the logic for a particular state is not spread over several functions. We do this by representing states as subclasses, all of which implement a particular interface inheriting from an abstract base class. As an example, let's consider membership. For example, subscribing to a website. There may well be several classes of membership, such as basic free access, an ordinary subscriber, and a premium subscriber. The type of membership a user has will determine their access to features of the site. We might think about using inheritance to model the various membership types, with 3 member types inheriting from a base class. But this will work until we need to handle upgrading a user's membership. How do we convert a basic member into a premium member? An object in C++ cannot change its type, and client code may have a pointer or reference to this object, so we mustn't do anything that would invalidate it. Thinking more deeply about the problem, we realize that if this property of the member class can change over time, then inheritance isn't the right way to model it. The membership type is actually a role that the member is playing, so we might decide to have a data member that holds the membership type. So here is a class called member, and you can see that it has an enum called membership and a variable that holds the current membership type. If we want to upgrade, we can add a function that switches on the membership type, and you can see that if we're at free membership, we can go to basic. If we're basic, we can go to premium. But if we're at premium, then we're as far as we can go, and we can't go anywhere else. This solves the upgrading problem, but what if the number of downloads that a user can have in a day depends upon their membership tier? We can add another function called canDownload that checks this, and we see that we end up with a function that has the same structure. We switch on the type, and if it's free, then we have 1 download. If it's basic, then we can have up to 5, and if it's premium, then we're basically unlimited. If we go on adding code to this class, then we're going to end up with switch statements in a number of functions. It's going to get more complicated. And our code for a particular state, for a particular membership type in our case, is spread out throughout the class. How can we solve this? We could solve this by representing each of our membership types as a subclass. So let's go and have a look how that's done. We have a class called membership. We've got a name, which is the type of membership that we've got, and we have a couple of virtual functions that we can overload. We have number of downloads per day that the particular type is allowed, and we have a function to upgrade. And then we have subclasses that represent our membership types. So we have, for instance, the free tier, whose name is free. It's allowed 1 download per day, and the code here can upgrade you to basic membership. And the same thing, basic member can upgrade you to premium, and premium doesn't go anywhere else. Now we've got the logic for a particular state within a class. And our implementation of member changes slightly because now member has a pointer to the current membership type. It's initialized to free membership, but we can upgrade. And notice that if we want to upgrade, we ask the current membership type, hey, how do I upgrade to the next tier? And it tells us. We don't have to know here. Likewise, if we are wanting to download, then we can say to our current membership type, how many downloads am I allowed per day? And that'll let us decide whether we're allowed to do that or not. Member doesn't need to know about the different membership types. It just delegates there. There are several things to note here. First, there are always trade-offs when using patterns. And in this case, the increase in modularity is balanced against an increase in the number of classes and the extra indirections required. Secondly, the knowledge of the next state is hard-coded into the state classes. So if we were to change the hierarchy and add another type of membership in, we might have to edit code in order to make this work. This could be improved by something like using a lookup table. And finally, each of our membership objects represents a single state, and as we've got it here, is invariant, so these could be represented by singletons. And that would also fix the memory leak that you may have spotted when we create a new object for each change of state. Maybe we'll see this when we come back and look at Singleton very shortly. The PIMPL, or Pointer to Implementation idiom, provides a way to hide the implementation details of a class so that the implementation's details and dependencies don't pollute the class interface and its header file. This has a number of uses, one of which is improving compilation speed, since the compiler doesn't have to recompile when implementation details change as long as the class interface remains the same. Typically, implementation is placed in a separate class with the main interface class containing only a pointer to the implementing class. Let's see how this works in code. So here's an example of a simple class that implements a container. You can see that it has a size and it provides square brackets operators to access elements held in the container, but what we don't have here are any details of how it's implemented. What we do have is a forward declaration to a class called impl and a pointer to an instance of impl. This is going to hold the implementation. So this means that any class that includes pimpl.h to use container doesn't need to know anything about the structure of impl, it just needs to know the class name. You might like to note also here that I've made this container class non-copyable in the traditional way by making the copy constructor and assignment operator private. So let's go and look at the implementation. Here we have the implementation of the inner class, and we can see that we have a class called impl that is a member of container. It takes a size and it uses a standard vector to hold its data. That member's public, but it's only going to be used from the enclosing container class of which it's a private member. Using a vector is an implementation detail. You might want to change it later. And since the container class only has a pointer to impl, changes in the implementation won't require recompilation of any code that uses container. We can also see how the container itself creates a new implementation object on construction and delegates operations to the implementation. If we have a look at how this is used, we can include pimpl.h and then create a container. But we know now that the main file here only has a pointer to the implementation. It needs to know nothing about how it's actually implemented. The trade-off here is that we have another level of indirection and more complexity in project structure. But in larger projects, this can speed up compilation considerably. If you look at UML and some of the details of implementation, you'll see that it looks quite similar to the state and strategy patterns. And indeed, they are very similar in how we would tend to implement them. But what's important here is the intent of the design and not what it actually looks like in code. Smart pointers provide a way to manage resources, but the concept of what a resource is and what management means is very broad. They're now very widely used in C++, and you rarely see raw pointers in modern C++ code. A class that implements a smart pointer overloads the arrow or crow's foot operator, giving indirect access to an internal pointer that it manages. So let's see a couple of ways in which simple smart pointers can be implemented. As a first example, let's create a smart pointer to manage the lifetime of a dynamically allocated object. Consider a simple class that represents a resource of some sort. It has a constructor, a destructor, and a method that does some work. If I create one of these dynamically, I must remember to delete it when I'm done. Deterministic manual memory management is very powerful, but it is the responsibility of the developer to free objects at the right time, else you risk getting a memory leak. So we can write a smart pointer class that will help us with this lifetime issue. Here's a class called PTR that contains a single pointer as its data member, and it's most usefully implemented as a template class because we aren't concerned with what the type of the pointer is. They all work exactly the same. So we pass the class a pointer in its constructor, which it stores away, and client code gets access to the managed pointer using the overloaded arrow and dereference operators. Note that the copy constructor and assignment operator are made private in the traditional way because we don't want anyone copying these objects. One smart pointer manages one object, and allowing copying will soon create problems for us. Having changed the main program to use this, we can see what the code looks like now. We now create a pointer and initialize it with a new resource object. We can then call methods on the resource object as if the pointer wasn't there at all. But note that what we don't need to do is manually delete the resource object when we're finished. When the pointer object goes out of scope, PR, then it will free up the resource object. And we can see this by running the code. We can see that I create the resource. When we call the method, I'm doing something, and then the destructor does get called on the resource object. This is quite useful, but there are quite a lot of issues with this simple implementation. For instance, what if you want to pass one of our smart pointers into a function? Well, you don't want to copy it or pass a reference because that will quickly lead to lifetime issues, and we'll have more to say about this later on. But before leaving smart pointers, let's look at another possible use, as sometimes lazy initialization is useful, deferring creation of an object until it is first used, and we can use a smart pointer to do this. The PTR2 class is very similar to the original, but if you create an instance and don't give it a pointer, so it ends up with a null pointer as its member, then it will create one before giving it back to the caller. So you can see here in the arrow operator and in the dereference operator a check and creating of a new default instance. We can have a look in our main function and see now that we just create a PTR2 object. We don't give it anything, and then when we call do something, as we can see when we run the code, it creates a resource and does something, and then it gets destroyed when PTR2 object goes out of scope. This can be useful when we have some sort of resource that we may want to use, but we're not sure, and we don't want to create it until we finally use it. So as a final thought, you shouldn't really be implementing smart pointers yourself nowadays, and finding homegrown smart pointers in a code base may well be a code smell, because we've now got good implementations in the standard library, and workable versions have been available for years in libraries such as RogueWave and Boost. Just be careful if you're playing with smart pointers that you don't end up reinventing the wheel. You've already heard how CRTP, the curiously recurring template pattern, provides a way to implement static polymorphism and removes the need for virtual functions. It does this by defining a templated base class that uses a derived class as its template parameter. So let's see how this works in practice. Polymorphism is typically implemented using virtual functions, as shown in this example here. Class base defines a protected pure virtual method getValue that is overridden by class derived. This enables base to have a non-virtual member that is implemented as a call to a virtual function in the derived class. Note how the protected function in the base class is changed to private in the derived class because this is an implementation detail and doesn't need any visibility. When I run the code, you can see that it works as expected. It calls the derived class method, which returns the value that we expect. Now, this is the way that many libraries are implemented, but there is a runtime cost in using virtual functions, and that may be prohibitive in low latency applications. We can see this if we look at the generated code in a debugger. I've loaded the binary into LLDB, which is the debugger for the LLVM compiler on the Macintosh, and which allows me to execute and disassemble code. The -n main command disassembles the function called main, and you can see the assembly code here. You don't need to understand the assembly code, but note the amount of work that is done before the call to return data, which I'm highlighting here. And you'll see there's a considerable amount being done up to this point. We can use CRTP to avoid the overhead of the virtual function call. You can see that the base class is now templated with the derived class as its template parameter. Now this time the getValue function isn't declared in the base class, and it's not virtual in the derived class either. Note how the base class has a helper function called derived that returns a reference to the derived type by casting the this pointer. Although it's not strictly necessary in this example, it will help writing tidier code in larger classes and prevent code duplication. So switching to main, we can now create an instance of the base class parameterized on the derived class, and this will create a static binding to getValue on the derived type. When we run it, as we'd expect, we can see the derived class function is called. If I load this version into LLDB and disassemble the main function as before, you'll see that there's a lot less going on before the call to return data, only half a dozen instructions or so. And that shows that using CRTP has a lot less overhead than using a more traditional virtual function. Singleton is a very interesting pattern to consider. Quite apart from the philosophical discussion about what we might mean by one, there are a number of very different ways to implement this pattern in C++, as well as some C++ specific issues. So let's see how they work in C++. The traditional implementation consists of a class that contains a static pointer to a single instance, together with a static function that creates it on first call. Note that we'll need a private constructor to stop people making instances themselves, and we also need to disable copying for the same reason. Now, although this works, this implementation isn't thread safe since there's the possibility of a race condition between the check in the if and the creation of the new instance. A common fix for this is to modify the function to implement double-checked locking. Here in the DCL Singleton class, we first check to see whether the instance has been created. If not, we then acquire a lock in the form of a mutex. And we then check again, so this is the double check, just in case the instance has been created since the previous check. If it hasn't, then we know that we can go ahead and create the instance because no one else can acquire the lock. And we can see this being used here, and it works just fine. Unfortunately, this is broken in C++ prior to C++11. Modern compilers can and do reorder instructions in order to make the best use of the processor, and this means that you cannot be certain that instructions will be executed in the order in which you entered them. Guarantees about exception order are provided by a memory model, which C++ had to specify in order to support the concurrency library, and this means that double-check locking can now be implemented safely, as we'll see later. So for now, be very careful about using double-check locking in older concurrent C++ code. Our last variant on this pattern is the Mayers singleton, an implementation due to Scott Mayers. This uses a static instance inside a function, and as you know, such an instance is initialized on the first call and thereafter lives for the lifetime of the program. It's interesting to note as well that this implementation returns a reference to the instance rather than a pointer. And if we switch back to main, we can see here that we can get a reference to an instance and then call the doit function, and it works absolutely fine. However, while this is useful and helps with lifetime issues, it isn't completely safe because the order of destruction of static objects means that it's possible for a client to end up with a dangling reference. And finally, on the topic of singletons, there are several C++ specific issues. One particular one is that of lifetime. How and when should we destroy the instance? The traditional implementation of singleton holds a pointer to the instance, but we know that dynamically allocated objects don't get destroyed at end of scope, and it might be desirable to destroy this dynamic allocated object at some point. Should the destructor be private, so that clients can't delete the instance, or public, so they can? Since it's the responsibility of the singleton class to create the instance, it seems reasonable that it should also handle deletion. But clients may want to delete the instance themselves. And if they do, how does the singleton class know that its instance has died? This can get quite complex. Now, in addition, the use of inheritance with singletons is complicated when static members are used. But really, you should be questioning whether an inheritance hierarchy of singletons is actually a good idea at all. And then, of course, there's multi-threading. You've already heard about the problems that can arise due to lack of a memory model prior to C++11, and this doesn't only apply to creating the instance, but to accessing it. So if you have a single instance being used by multiple threads, you're going to have to be very careful. I hope this section has shown you that, although singleton may seem like a simple pattern, there is a lot to consider when implementing it in C++. But C++11 has introduced some new features that make it easier to implement singletons, and we'll meet some of these later in the course. Now that we've seen how patterns and idioms can be implemented in C++, try implementing one for yourself. Research and provide a sample implementation and a demonstration application for the chain of responsibility pattern. There are a few things to watch out for. First, make sure that you don't confuse chain of responsibility with decorator, both of which are implemented using a chain of objects, but which have different intents. Secondly, what's going to happen if a request reaches the end of the chain without being handled? And lastly, think about how you're going to build the chain and link the individual objects together. You can find a sample implementation for this exercise in the working files for this chapter. We've seen how patterns can be implemented using traditional C++, but releases since 2011 have added a number of features that have a fundamental impact on how we write code. Let's start with a brief recap of C++'s versions and then see what they've added to the language. Although C++ has been around for some time, the first standard was issued in 1998, and this defined what we can think of as traditional C++ and included classes and templates. 2003 then saw a minor update that consisted mainly of bug fixes, and this was followed by a major development program which took 8 years and added a large number of significant new features to the language. We'll be looking at these and how they affect the way we write code in the rest of this section. Because it took such a long time to arrive at this release with the goalposts shifting frequently, the Standard Committee set a schedule for a release every 3 years, so we saw the release of C++ 14. This mainly provided bug fixes and improvements, but had little in the way of completely new features. So a 3-year release cycle means that we'll see releases in 2017 and 2020. The feature list for C++ 17 is still being finalized, but is likely to include support for networking, modules, coroutines and ranges, while the 2020 release may include a standard 2D graphics library. Let's quickly run through the new features that were introduced by the C++ 11 standard. You'll see that they have significantly updated the language. 2 changes were made to the way in which objects are constructed. Delegating constructors let one constructor call another, while inheriting constructors let a derived class initialize itself using constructors from a base class. Both of these can help reduce code duplication. 2 keywords have been added to control how class member functions are handled. The default keyword tells the compiler to generate the default implementation, such as a default copy constructor. This is usually redundant, but it can be useful where you want the default version to have a different access level to normal. The delete keyword tells the compiler not to generate a default version, and now provides a more efficient and better documented way to inhibit default creation and copying. There have been major changes in the area of initialization. Uniform initialization means that just about any data structure can be initialized using the same syntax, so that, for example, a vector can now be initialized in the same way as an array. This also applies to object construction, so the same initialization can be used when calling an object constructor. The area of R values has perhaps had the greatest effect on how developers write C++, particularly those who are writing libraries. C++ now lets you take a reference to a temporary, an R value, which hasn't previously been possible. Function overloading lets you distinguish between normal and R value references, and this is very useful because if you know you're dealing with a temporary, you can steal its state rather than have to copy it. This is called move semantics and has hugely improved the efficiency of code in the standard library. The explicit keyword can now be applied to conversion operators as well as to constructors, and that helps avoid unexpected conversions. And type inference is now supported through the auto keyword. We also have decal type, which deduces the type of a variable or expression. You can use this to declare a variable that has, for example, the same type as x times y, and this is particularly useful in templated code where types are only known at compile time. Lambdas, or anonymous functions, are a particularly useful addition to C++. Not only can they make code more concise and easier to understand, but they're also necessary if one is going to program in a functional style. The range 4 is a relatively simple addition, providing a high-level way to iterate over collections of all types, and this idea is supported by many languages. It's also possible to write custom classes that will work with the range 4, which helps make code more usable and maintainable because you no longer have to wonder just how you're going to iterate over a custom collection. C++ now has a value to represent a null pointer. This is null_ptr, which is a proper pointer of type null_pointer_t. Prior to this, developers had to use either the null macro inherited from C, which is implementation dependent and necessitates including header files, or 0, which makes a null pointer an int, and that can cause problems. The constexpr keyword provides support for generalized constant expressions, which means computation at compile time rather than runtime. An obvious example might be a function to add 2 numbers. If it is marked as constexpr, the compiler may be able to compute results for calls such as add 2, 2 at compile time, so there is no runtime overhead. A static assertion is one that is checked at compile time rather than at runtime. This can be used together with type traits, which enable the compiler to check properties of types. These are especially useful when using templates, as they give the developer control over the types used to instantiate the template. Speaking of templates, there are two main changes in this area. Variadic templates are perhaps the most advanced feature introduced by C++11, and they provide a way to construct templates having variable numbers of arguments. And finally, template aliases, which not only allow you to provide aliases for template types, but more usefully, to provide aliases with parameter types already bound. A number of new features have been added to the standard library as well. A number of new containers, including hash tables, tuples, singly linked lists, and fixed size arrays. That last one is interesting because it is a wrapper for a built-in array that allows arrays to support all the standard container operations. A number of new algorithms have been added as well, such as all of and any of to check a predicate against values in a range, copy if, move, is sorted, and various others. The standard smart pointers have been completely upgraded, replacing auto pointer, which was never very satisfactory. Unique pointer provides a single owner smart pointer, while shared pointer allows shared use. A weak pointer holds a reference but has no concept of ownership, and that's useful in scenarios such as caches. And although it isn't widely known as a functional programming language, C++11 has added features that make it easier to program in a functional style. Function is used to represent a callable target, which can be a function pointer, a function object, or a lambda, and this makes it much simpler to manipulate functions. Bind provides a mechanism for partial function application, taking a function, binding one or more of its arguments, and then returning a new function. We'll see how these can be used in functional programming later in the course. And last but not least, C++ now has support for concurrency. Prior to C++11, all concurrency functionality was platform dependent, making it hard to write portable code. That's no longer the case. So let's look in a little more detail at some of these features that are particularly relevant to how we might implement design patterns. The range-based for, smart pointers, lambdas, move semantics, function and bind, and variadic templates. The range-based for loop is designed to iterate over a wide variety of containers, including built-in arrays, strings, and STL containers, and it'll also work with other classes, provided that they implement STL-style iterator functionality. This construct abstracts away the underlying looping mechanism, working at a higher level, and that makes for cleaner code and also helps avoid off-by-one errors. And we can see it working here, where we create and initialize an array, and then iterate over each element using the range-based for. The new smart pointer classes, unique pointer, shared pointer, and weak pointer, provide a robust way to manage resource lifetimes and should be used in preference to manually calling new and delete. Let's see an example of how these can be used. So here is a simple class X that holds a single integer and has a getter to return it. The constructor and destructor have been instrumented so that we can track the lifetime of instances. What we want to do is create an object dynamically and pass it to a function, and the function is going to use it and then delete it when it's finished. Now this works, and we can see here the object being destroyed, but we need to make sure that we remember to delete the instance at the right point, and in much more complex code this can be a problem. A unique pointer will manage this for us. We now create a unique pointer to manage the instance and change the function signature to accept this. The call to move tells the compiler that the object can be moved from, so its state is moved into the function argument. This ensures that the unique pointer in the function takes ownership of the dynamic object. When this unique pointer goes out of scope, it will delete the instance it's managing. Note that the argument is by value and not by reference. Move semantics mean that we aren't taking a copy. Once we've called the function, we can use assert to show that our original unique pointer no longer is managing the object. So let's run this, and we can see that the object is indeed destroyed on leaving the function, and that our assertion worked, showing that we did indeed hand over ownership. Lambdas are anonymous functions, much used in functional programming and with STL algorithms, as we can see in this example. As well as letting you write shorter and more readable code, they have a couple of other important advantages. Firstly, lambdas can have very little runtime overhead. A lambda is converted to a function object, and if properly written, all its code can be inlined. Secondly, lambdas are closures, which means that they can have access to variables that are in scope when they're defined. Let's see an example of this. Here is a small function that is designed to sum the values in a vector. The forEach function takes the beginning and end of the range and a lambda that it calls for each member of the vector. Looking at the lambda in more detail, the square brackets are called the lambda introducer, and they can be used to list variables in the outer scope that you want to use or capture within the lambda. In this case, we want to use sum, and the ampersand shows that we want to use it by reference rather than by value. The round brackets then contain any parameters the lambda may need, followed by the body in parentheses. If we run this, we can see that a vector containing 3 elements is summed to give the correct answer. So what's the advantage of using a lambda? One advantage is code locality. Instead of creating a named function that we may only be going to use once within the forEach, we can define the function at the point of use. And as I've already mentioned, lambdas can be very efficient due to code inlining. The introduction of R-value references and move semantics has greatly improved our ability to write efficient code because it is no longer necessary to copy data out of temporary objects. Temporary objects are often passed as arguments to copy constructors and assignment operators, and being able to overload on R-value references means that we can write more efficient classes. So let's see how this works. To illustrate this, here's a simple class that contains a single dynamically allocated member. As you'd expect, this class defines the big 3, copy constructor, destructor, and assignment operator to manage the lifetime of the dynamic member. The class has 2 other members as well, a move constructor and a move assignment operator. These use the double ampersand notation to show that their arguments are R-value references. I've added logging to these functions so you can see which ones are being executed. And I've also defined an operator plus in order to add 2 Y objects and create a new one. Going back to main, we create a couple of variables and now play with them. Notice how I set variable C equal to B. Since B is an L value, this will call the normal assignment operator. Variable D, on the other hand, has the result of an expression assigned to it. Since this will be a temporary, the move assignment operator will get called. And indeed, if we run the code, we can see that that's the case. Here is the normal assignment operator for the first case and the move assignment operator for the second case. Looking at the implementation of these operators, you can see that the move assignment simply swaps 2 pointers, while the normal one will need to perform an allocation when creating the variable TMP. Simply being able to steal the content of a temporary can make for much more efficient code, and the standard library now uses this wherever possible. These 2 functions help support a functional programming style, as we'll see shortly. Function represents any callable object, which could be a traditional function pointer, a function object, or a lambda. Bind is used for partial function application, taking a function, fixing one or more of its arguments, and returning you another function. Let's see how to use them in code. We need to include the functional header in order to use function and bind. I've started by defining a simple add function and a class called op that defines its own function call operator, and you'll see that these 2 are functionally equivalent. In main, we can now create a standard function object. So this is a templated type, and the template parameters describe the signature of the function that it can be bound to. The first parameter is the return type, with the argument types following in parentheses. So in this case, I can bind f to any function that takes 2 ints and returns 1, and that obviously means that I can use it to call the add function. And you can see that it is executed just like the function itself. We can also bind f to an instance of class op, since it defines the function call operator, and since a lambda satisfies the requirements as well, we can bind to those. So a standard function object implements the idea of a callable object, abstracting away the detail of exactly what it is. And if we run this, we can see those working. The bind function lets you fix one or more arguments to a function, returning you a new function object. This technique, using an existing function to create a new one, is commonly used in functional programming. Supposing we have the add function, and we want a function that will always add 3. We don't need to write a completely new function. Instead, we can use bind to fix one of the arguments so that it will always be 3. And in the process, we will turn a 2-argument function into a single-argument function. Let's see how this works. Note how the call to bind is constructed. The first argument is the name of the function we want to bind, in this case add. And this is followed by further arguments which represent the arguments to add itself. And you'll notice that the first one has been set to 3, while the second one is set to a placeholder, _1, which shows that we want to use the second argument as it is. These placeholders are defined in the standard placeholders namespace, and they run from _1 to an implementation-defined maximum. I've added that at the top of the source file. And the result of the call to bind is another function object, but this time it's one that takes a single integer and returns it, showing that we have now got a single argument function being called. And if we try calling this with 3, sure enough, we can see that we get the answer 6. We've got our function that adds 3 every time. Variadic templates provide developers with a way to write type-safe functions and classes that have variable argument lists. Previously, implementing functions like printf and scanf was not type-safe, because there was no way to check the type of the arguments that you were being passed, and in the case of printf and scanf, that the type of the arguments matched the format specifiers. Using variadic templates, the compiler resolves the types at compile time, and it's possible to check what you're getting using type traits and static assertions. So let's see how this works in code. As a very simple example, here's the add function rewritten as a variadic template. The first template parameter is going to be the type of the first argument, and the template ... is called a template parameter pack, and that holds all the remaining type parameters. You can see that the result of the function is the value of the first argument added to the result of calling add on all the rest of the arguments, and this is terminated by providing a specialization for a single argument. As is usual with templates, this will work for any type that defines a plus operator, although we could use static assertions and type traits to check exactly what we're working with. It's important to note that this isn't recursion, although it looks like it. Because we're using templates, the compiler generates a new function for each level, and inlining means that this can be very efficient. So let's run the code and see that it works. And as you can see, our add function adds 3 numbers and comes up with 6, and also concatenates the 2 strings. There is a lot of material available, both printed and online, and I'll point out some useful resources here. Effective Modern C++ by Scott Myers is an update of his well-respected Effective C++ book, updated for C++ 11. It's a very good read for anyone wanting to see how the new features should be used. Modern C++ Design by Alexandrescu is a classic, and while not specifically written about patterns, reading this will expand your knowledge of C++ considerably. C++ Concurrency in Action by Williams provides a very good introduction to C++ 11 features, such as R-value references and move semantics, in the context of discussing the concurrency support provided by the standard library. This is another book that is well worth reading even if you don't have an immediate need to write concurrent code. It's hard to know where to start when discussing online resources because there's so much to choose from. ISO CPP is a good place to go for news about C++ and where standardization is going. The status page gives details about what to expect in forthcoming releases. Bjarne Stroustrup site has a very comprehensive FAQ page on modern C++. The CPP Rock site, as well as a lot of other interesting material, has this overview of what was new in C++ 14. Arne Mertz has a useful blog on writing clean and maintainable C++ code, and you're bound to find a lot of interesting and challenging articles. And finally, if you don't already know it, CPP Reference is one of the best sources for online reference material on all versions of C++. So what is functional programming, and why does it matter to C++ developers? Functional programming is a style of programming that focuses on function execution as its main computational mechanism. It's been around for a long time, since the 1950s in fact, but is gaining popularity much like object orientation did in the 1990s. This is mainly for two reasons. Firstly, it gives a very concise and efficient way to write algorithmic code, and secondly, it can make it simpler to write concurrent code. You'll find that functional programming introduces many new patterns and renders some existing ones obsolete, and that's one of the reasons why I'm covering it here. Functional programming is supported by a number of languages, notably Haskell and the ML family, but it is possible to program in a functional style in C++ by following some principles. You'll also find that some of the features added in the C++ 11 release make coding in a functional style much simpler than before. Well, one reason to look at the functional style of programming is that object-oriented programming, although very useful, is not enough. Firstly, OO isn't good at composing algorithms, building functions together to solve problems. OO data structures are often slow, and typical OO code with its tendency to mutate shared state often doesn't handle concurrency well. Although it isn't easy arriving at a definition of just what functional programming is, there are a few principles that everyone seems to agree on. The first is the concept of functions as data, where functions are objects and so can be passed around and operated on. They can be passed to functions as arguments and used as return values. Functions that operate on other functions are called higher order functions. Functions are also used as building blocks, with simple functions being composed into larger constructs. C++ has always had this to a certain extent in the form of function pointers, but now we have function and bind in the standard library, which are far more powerful and expressive. The idea that data is immutable is another fundamental principle. Once created, an object doesn't change state, and if a state change is required, a new object is created. Strings in Java and C# already work like this, and it has several advantages. Firstly, it greatly helps with concurrency if you know that a variable or collection isn't going to change while you're using it. And secondly, it helps when reasoning about code because once created, you know what the state of a variable is going to be from that point on. Now, you might think that creating a copy every time a variable changes state is inefficient, but that isn't necessarily the case. Let's consider a simple linked list where we have a pointer, p, to the first element. If we want to add an element to the head of the list, then this is simple. The new element links to the rest of the list. No copying is required, and most importantly, the original pointer p is still valid, pointing to the original sequence, while pointer q points to the new sequence. But what if we want to add a new element to the tail of the list? In this case, we have to copy the list if pointer p is still going to be valid. Although working with data structures immutably can be efficient, you still have to understand what's going on. Moving on, no side effects means just what it says. Execution of a function doesn't affect anything outside the function itself. A function that adds two integers is a classic example, giving you the result and not changing the arguments or anything else in the environment. Functions that have no side effects are called pure functions. Unfortunately, not all our functions can be pure because operations such as throwing exceptions, performing I/O, and even changing a memory location are side effects. And if everything was pure, we wouldn't be able to interact with the program at all. So it's common practice to write code with a pure core and an impure outer layer that handles I/O and other impure operations. I'll mention how we can handle exceptions in a pure way towards the end of this section. Now, we don't just want immutability of data, we also want immutability of execution, so that calling a function with the same arguments always gets the same result. This makes code easier to reason about and has other advantages as well. If we always get the same result for a given input, and that input might be used again, then it may well make sense to cache the result to improve performance. In a similar vein, always getting the same result means that we can replace a function call by its result. For example, it's perfectly safe to replace 2 plus 2 by 4. There are some other consequences that you might not have thought about. Supposing that we have two expressions, as shown here. These two don't contain any terms in common, and as a result, they could be evaluated in any order. Further, if the expression is pure and the result A isn't used anywhere else, then the entire expression can be removed without affecting the rest of the code. And lastly, since the two expressions are independent and don't affect anything else, they could be executed simultaneously. Lazy evaluation is another characteristic of functional programming languages and simply means not calculating something until you need it. This is useful with chained transformations, where, for example, we want to add 1 to each number in a list and then square each resulting value. Traditional eager evaluation will transform the original list and then apply second transformation to get the result. Lazy evaluation will apply the two transformations element by element, so that it will add 1 to the first element and then square it. This is obviously useful if you have a list of 1,000 elements and only end up needing the first 5. It's also useful where you have sequences of an indeterminate or even potentially infinite length where you can't operate on the entire dataset because you don't have it all. But there is a downside to lazy evaluation, and that is that it can make performance hard to predict because you don't know exactly when an expression is going to be evaluated. And lastly, recursion. This is familiar to most programmers, but writing code recursively is very common in the functional world for several reasons. The first is practical and is related to immutability. If variables are immutable, then you can't write a traditional counted loop, and you have to look for another way to handle looping, which recursion provides. Secondly, you don't see many explicit loops in functional code. Loops are imperative, with you telling the compiler exactly what to do. Functional code tends to work in a more declarative way, expressing the intent of the code without necessarily telling the compiler how to do it. And thirdly, recursion is a natural way to express some algorithms, as shown in this example, simple calculation of a factorial. One of the problems with recursion is that each call typically requires a new stack frame, and you can run out of stack if you recurse too deeply. A technique called tail recursion, in which a set of recursive calls is converted to a loop, is supported by almost all modern compilers and results in highly efficient code. We're now going to look at 3 typical functional operations that can be considered functional design patterns because they're used to solve frequently occurring problems. We'll see a little later how these can be implemented in C++. The first of these is filter, in which we select elements from a sequence based on whether they match a predicate. Good examples might be all the customers who live in London or all the stock trades greater than a particular value. So let's take a sequence of integers, and we can use a simple predicate to match even numbers. Applying this to the original sequence results in a new sequence that only contains the even values. Because we aim for immutability, the original sequence is not changed, and the result is a new sequence containing copies of the even values. Filter is often the first operation applied in a chain because it will tend to reduce the amount of data processed by succeeding steps. Our second operation is map, in which an operation is applied to each element in a sequence, resulting in a new sequence. Suppose that, once again, we have a sequence of integers, and we want to add 2 to each element. The map operation creates a new sequence containing the transformed values. It's important to note that, following our principle of immutability, map creates a new sequence and leaves the original unchanged. The map operation expresses the intent but doesn't tell the compiler how to do it. So if the original sequence is immutable, it might be possible to transform the elements in parallel, giving a performance improvement. Map is also related to the for each function that you may be familiar with. The difference is that map creates a new sequence without any side effects, while for each is normally executed for its side effects, such as printing a value. And as an aside, these functional operations sometimes remind people of a select statement in SQL, where you're telling the database what data you want, but not telling it how to do it. And in fact, SQL does work in quite a functional way. Our third operation is reduce, also called fold in some languages, which is used to combine all the elements of a sequence into a single value. One example might be concatenating a list of words into a single string, and another, finding the total value of a collection of trades. Suppose that we have a list of integers which we want to sum. We can express this operation as follows. Given A and B, give me their sum. The reduce operation starts with the first 2 elements as A and B and applies the operation to them, resulting in 5. It then takes that result as A and the next value as B, applies the operation to that, and that gives us the final value 11. Now this will obviously work with any data type that supports the plus operation, and you might have realized by now that these 3 operations are high-level abstractions. Reduce is an abstraction over the concept of combining. Map is an abstraction over the concept of transforming, and filter abstracts the concept of selection. Although C++ was not designed as a functional language, we can go quite a long way towards writing code in a functional style. The STL, with its collections and algorithms, can help focus on a functional rather than class-based style of coding, and code can be designed to use immutable data and pure functions. And some features of the standard library can help us to use the functional operations that we've discussed. Remove copy if uses a predicate to remove items from a sequence, returns a new sequence, so that can be used for filtering. Transform applies a function to each element in a range, returning a new range containing the transformed elements. This allows us to do map operations. And accumulate performs a reduce operation. The default uses the plus operator to sum a range, but an overload can use another binary function. C++17 will introduce a function called reduce, which is a more efficient version of accumulate. Now, although these functions are useful, the standard library wasn't written with functional programming in mind, and there are a couple of problems. Function composition, for example, passing a collection to filter and then through map and then through reduce, is ugly and inefficient. And laziness is not supported, so that chaining operations together will end up creating intermediate temporary collections. Two libraries can help with this: Boost Range and Range v3, which have been written specifically to address these and other problems. And some of this work may well make it into C++17, which will greatly help when writing functional code. And finally, a word about exception handling. Exceptions are not functional because they are a side effect. A function should always return a value and should not suddenly dive off somewhere else if an error occurs. A technique adopted by many functional programming languages is for a function to return either the result or an error. In the case of C++, that means returning an exception object rather than throwing it. Apart from predictability, this has the advantage that the representation of the error, the exception object, is separated from the mechanism used to handle it. The caller can now choose when and how to process the exception. So C++17 will introduce optional T, a type that may or may not contain a result. Here we see how it would be used. A function that tries to parse a string into an integer may or may not be able to do that, and it will return an optional which may or may not contain a value. This type, which is similar to C#'s nullable, is useful to indicate that a function cannot return a result, but it doesn't tell you what the problem is. Andrei Alexandrescu has created expected, a variance type that contains either a result or an exception object, thus enabling us to handle errors in a functional way. Not a lot has been published on functional programming in C++ yet, because it is a relatively new topic. There is a book being written, due to be published in mid-2017, but it isn't complete yet. An interesting talk was given by Nicola Gigante at the Meeting C++ conference in 2015, and the slide deck can be found online. But a lot has been written on functional programming that isn't specific to C++, some of it more helpful than others. The first two links here are general discussions about what functional programming is, and you can find many similar articles online. And if you're not worried by math, Bartosz Chmielewski has written a great series on category theory, a branch of mathematics that is highly relevant to functional programming. We've talked a bit about the new features in C++ 11 and 14 and functional programming. So let's see some examples of how these can be used to improve the way in which we implement patterns and idioms. We're going to look at 5 examples: RAII, PIMPL, observer, functional idioms in the form of map, filter, and reduce, and functional error handling. We saw earlier how RAII, the resource acquisition is initialization idiom, can be used to manage resources by undoing in the destructor an action that was undertaken in the constructor. If you're using RAII to free a dynamically allocated object, consider using smart pointers instead of doing it yourself. As I've mentioned previously, you should not be seeing delete used very often in modern code. So let's see an example of how we do this. We start with a simple class called value, which contains a resource that needs to be managed. In this case, it's simply an int, but it could, for example, be an object representing a connection to a database. Instances are identified using an ID that's a simple incrementing value. That isn't thread safe, but it doesn't need to be in this example. In real life, you could generate an ID using the atomic operations introduced in C++ 11. Now let's look at the traditional way of managing a value object. The implementation of the class PTR allocates one in its constructor and deletes it at end of life. But let's suppose that it also needs to support several other operations based around the idea that a value can only be managed by a single PTR at a time. These operations are no copy construction or assignment, move construction and assignment, giving up ownership of the value object, getting the value object, deleting the currently held value object and using a new one, and swapping the value objects between two owners. If you look through this code, you'll see that it has to juggle pointers carefully and that there are two uses of delete. So let's see how we could rewrite this using smart pointers. PTR2 replaces our manual memory management with the standard library's unique pointer, which we can use to ensure that our value object is never accessed by more than one owner at a time. In the constructor, I could just use unique pointers constructor to create an object that wraps a value, but the make unique function is more efficient and also provides better exception safety. As an aside, if you're using CLion, as I am here, you may occasionally see an error being reported by the code editor. This is actually a bug and the code compiles and runs perfectly well. You can see how the move constructor uses release to steal the content of its temporary argument, while the move assignment does the same, using standard move to force a move operation. We obviously no longer need to handle destruction because the smart pointer does it for us, and so we don't need to implement a destructor. The other member functions are implemented using unique pointers methods, and this greatly simplifies the memory management. So we end up with simpler and shorter code, 41 as against 54 lines in the original implementation. Let's see this in use. The main function creates two objects, f and f2, which will in turn create their own dynamic members. And you can see that we've got some code here to print out the addresses held in each pointer at various places in the function. Copy construction and assignment won't work because we've disabled those. We can, however, use move to force a move assignment from f2 into f, and when we do this, the original object managed by f will be destroyed, and it will now manage the one that was owned by f2, which will in turn be empty. So let's see that when we run it. So here are two contained objects being created with IDs 1 and 2, and we can see that the values in f and f2 have these addresses. Note that the value in f2 ends in 28E0. When we do the move, the first object that was held in f is destroyed, and you'll notice that f is now managing the object at 28E0, and f2 isn't holding anything, thus showing that we are managing the memory through unique pointer. To recap, we know that the PIMPL idiom is used to separate the declaration of a class from its definition. We also know that PIMPL means pointer to implementation, and any time that you see mention of pointers, you should be asking whether you can use smart pointers. So let's see how we can use them in an implementation. As before, the container class holds a pointer to its implementation. Herb Sutter recommends using a unique pointer because this will handle lifetime issues and also because it reflects the intent that the implementation object should not be shared. There are a few differences from our previous implementation. The first is that we obviously don't need to delete the implementation object ourselves because the unique pointer does that for us. The second is that our implementation is not movable or copyable by default, and so we don't need to specify it. Although we explicitly declared them as deleted in the RAII example, we don't need to do this because unique pointer has deleted copy and assignment operators, and this prevents our class from being copyable. Switching to the implementation, we'll see that it's quite similar to what we had before. We need to define the class destructor, even though a default will do. This is because unique pointer needs to have a completely defined class in order to function. If the destructor isn't defined at this point, then the compiler would generate the defaulting calling code, but that's rather too late. Notice also how the smart pointer is initialized. As I said in the RAII example, using make unique is the recommended way to do this. If you want to call make unique, you'll need to set your IDE to use C++ 14, and if you're using CLion, you may get a spurious error from the IDE that you can ignore. The rest of the code, including the main function, is the same as before. Using unique pointer hasn't made a huge difference, but it has resulted in code that is simpler and removed the need for manual memory management. Observer is one of the classic design patterns. It's used to implement event-driven systems. There are a number of modern C++ features that will help us to implement it. We typically have a subject that wishes to be notified when events happen, so it registers itself with an observer. When an event occurs, the observer notifies all subjects that have registered themselves. So let's see how we can implement this. We start with the concept of an event, which is an object representing something that has happened. Events are therefore rather similar to exceptions, and it may be that the type alone tells you what's happened, but the object could also carry a payload. Here I have defined a base event class and two subclasses to represent concrete event types. The payload in the first class returns an int, and the payload in the second class returns a string. The subject class wants to be notified when events occur by having its handle method called. We could provide overloads for different event types, but here I am using a single method that checks the type of the incoming event and uses that to decide what to do. Note how I'm using type information to check the type of the event that I've received. We're casting the event reference to the appropriate type using dynamic cast. Now you may know that this throws an exception when a reference cast fails, but since we've already checked that the types match, this isn't something that we need to concern ourselves with. So now we have events and a class that wants to handle events. How do we link them together? The observer class provides the event dispatching mechanism through two functions, subscribe and notify. Subscribe is used to tell the observer that a subject wants to be told about an event and passes it a callback function. When an event occurs, we will call notify to tell the observer to use the callback to pass the event back to the subject. So let's take a closer look at this observer class. Callbacks are represented by function objects, and to save repeating the rather ugly signature, I've used a template alias to provide a nicer name. We may have more than one subject interested in a given event, so callbacks are stored in a map with the event type as the key and a vector of callbacks as the value. Type index is similar to type info in that it represents type information, but in a form that can be used as a map key. I'm using an unordered map here because it is faster than a map for lookups, and I don't need the keys to be in sorted order. You can see how the template alias makes for a nicer definition. Subscription involves adding a callback function to the vector for the appropriate key, and the only thing to note here is that the callback argument has to be an R value. You'll see why shortly. Notification is simple. Given an event, do we have a key with that type in the map? If so, iterate over the items in the value vector, calling each callback function. Finally, let's see how this can be used. Here, we create two subjects and an observer and subscribe to the two event types. Bind is used to create a function object that's bound to the handle on the subject, and that's passed through as an argument. But binding involves returning a new function object with its arguments bound. That will be a temporary, and that's the reason why the argument to observer's subscribe has to be an R value. And then finally, we tell the observer to send notifications for the two event types, and we can see that working when we run the code. We're now going to look at how we can implement three of the basic functional operations you saw in the functional programming chapter. The standard library contains a number of algorithms that can be used to program in a functional style. However, they don't fit 100%, and the syntax is often rather off-putting. So let's take a look at how we can implement three foundational functional operations: map, filter, and reduce, using algorithms from the STL. This will enable us to write code like this, which is readable and concise. The STL algorithm remove copy if can be used for filtering, but it isn't very intuitive. It copies elements from one container to another, removing the ones that match a condition. Here we have a vector v that we want to filter and a second vector that will hold the result. The next task is to define a filter expression as a function object. So is even is a predicate that tests whether a number is even. But for filtering, we want to copy the elements that do match the condition rather than the ones that don't. And rather than write another lambda, we can adapt it using standard's not one function and adapt a function that performs a logical NOT on the result of a unary function. That works fine, as we can see when we run it. We get the even numbers out as a result. But you may wonder why we don't pass the lambda directly to not1. If you try this, you'll find it doesn't work, and the reason for this is that not1 expects a standard function, and a lambda isn't actually a standard function. So we can implement filtering, but there are a couple of reasons why this solution isn't what we'd ideally like. First, it isn't very elegant. But more importantly, remove copy if doesn't return the new sequence, which will make it difficult to compose functions. Let's wrap this in a function that will make it easier to use. We will, of course, want to make this a template function so that it is as general as possible, both in terms of the collections we can work on and the predicates we can pass in. So let's move the call to remove copy if into a template filter function and add template parameters to represent the sequence and predicate types. We create the output sequence in the function and use it as the return value, and so this implementation is functional in that the input sequence is unchanged. We do have one issue though, in that the function that we pass to not1 needs to know the type of its argument, which is the type being held in the container. But since the container type is a template parameter, the compiler can't deduce this. Luckily, we can get the type from the value type trait on the container. Note the use of type name here, which is necessary because in a template class, the compiler doesn't know whether value type is the name of a type or a static member of seek. We can use this to provide an alias for a function and then use that alias to construct a function instance and pass it to not1. Let's see how this is used. So we can use our filter function like this, and I think you'll agree that it is easier to read and much more elegant than the original. One disadvantage of this simple implementation is that it doesn't work with standard arrays, because they aren't objects and don't support the features we need. But we could use standard array, a fixed size container that has the same behavior as a built-in array and which was introduced by C++11. I leave that as an exercise for you. Another advantage of this implementation is that it lets us compose filters. Suppose that we want a filter to get even numbers and then only want the ones greater than a certain value. Define two predicates, is even and is large, and then use nested calls to filter. This is much easier than using remove copy if. Now let's implement map. The structure of this function is going to be very similar to that of filter. We take a collection and a lambda. We apply the lambda to the collection, using transform this time, and then we return the resulting transformed collection. Once again, we pass in a lambda and use an alias to construct a signature of the correct type. I'm using a typedef here to stop the using statement getting too ugly. In order to use map, we need to define a lambda that represents the mapping operation. In this case, I'm just going to double the items in a collection, so the lambda takes a value and returns its double. Here we can see map being used, and we apply the twice operation to our vector v. What's interesting is that in true functional style, we can now compose map and filter, say, to find all the values greater than or equal to 5, and then double them. And when we run that, we can see the output from map doubling the values, and then when we compose map and filter, we're only doubling those values greater than or equal to 5. Note that this is rather limited in that the types of the original and transformed collections are the same. This often isn't the case, for example, transforming a list of strings and getting a list of string lengths, but I'm not going to develop this further here. Finally, let's see how we can implement reduce. This very simple implementation is actually just a wrapper around standard's accumulate function. As usual, the first template parameter is the container that we're working on. The second template parameter is the type of the result, which might not be the same as the type held in the container. The second actual parameter to the function is the starting value for the reduction. For example, if we're summing a sequence of integers, then we'll want to start from 0, but if we're multiplying them, then we'll want to start from 1. The final template parameter represents the operation to be applied, and this is a binary function. As explained in the chapter on functional programming, the two arguments are the result of the previous iteration, or the start value on the first one, and the current value. So let's see how this works. We can define a simple add lambda and use it to sum the values in our vector. Reduce is an abstraction over combining values, so we could use it to concatenate strings because that's logically the same operation. So we can define a vector of strings, and then we can define a lambda to concatenate them and pass it to reduce. This works absolutely fine, but you'll notice that both lambdas are almost identical except for the argument types. Before C++14, you had to repeat the lambdas, but C++14 introduced the idea of generic lambdas, and that allows us to define a generic add operation which will work with anything that supports the plus operator. So we can use add to sum up the values in our vector v. And of course, this lets us do useful things like let's define a vector of prices, and then we'll define a lambda that adds tax of 20% to each price. So we can use map to adjust our price vector, and then we can use reduce to sum the total. And if we run that, we can see that we get 71.64, which is the sum of our adjusted prices. Now, there are obviously a number of refinements that could be made to these very simple implementations in order to make them generally usable. But I hope you've got an idea of how functional programming concepts can be used and can be useful in C++. I mentioned in the chapter on functional programming that throwing exceptions doesn't really fit into the functional world. There's nothing wrong with using exception objects to represent errors, but throwing them and catching them elsewhere can be an undesirable side effect. So function should always return a value, and if it returns you an exception, then you're free to handle it when and where you want. This final example that we're going to see uses some more advanced and little known features of C++, and so I'll go through it in some detail. So we start with a simple conversion function, parse, which uses standard's stoi function to convert a string to an integer. If it can, it returns the integer, and if it can't convert, it throws an invalid argument exception. We can see how it's used. We try and convert valid and invalid strings, and exceptions are handled as we'd expect. We can see when we run it that 42 gets converted, but ABC doesn't. Functional style says that a function should always return and should always return a value. And we can do this by returning a type that will either contain the result or an exception. This sort of either-or type is common in languages that support a functional programming style, and we'll develop one here. The class I'm about to show you is based on Alexei Alexandrescu's expected class, but it presents a considerably simplified implementation that doesn't include all the functionality it would need in order to be fully useful. So we'll want a template class with a single parameter that represents the result type, because the possible exception will always be a standard exception or a subclass. Now, if you want an object that can hold one of two possible values, an obvious implementation choice is to use a union, which in this case holds a value of type t or a value representing the exception. As we'll see, this makes construction and destruction of these fields rather interesting because they aren't objects in their own right. What the union contains is a piece of memory that can be treated as a value or an exception. The type we use to represent the exception is a standard exception pointer, a smart pointer type introduced in C++11. It's useful in several cases, and here it will let you return exceptions from code that might be running on another thread. Normal C++ exceptions can be problematical to throw and catch between threads. You'll see that the class has two other private members, a default constructor and a discriminator called hasValue that tells us which member of the union is in use, or in other words, whether we should expect an exception or a value. We can construct an object from either a value or an exception. The first is done using a simple constructor, while the second uses a static function called fromException. So let's take a look at that. This needs a template parameter for the exception type, and the first thing it does is to create an exception pointer to wrap the exception that's been passed in. We can then create a result object and set its hasValue field to false, since we're storing the exception in the union rather than a value. The next line of code is interesting, though, and it uses a rather esoteric C++ feature called placement new. This form of new runs a constructor on a previously allocated piece of memory, which in this case is the union in the result object we just created. Here, we're telling the compiler to initialize an exception pointer at the address of the EX field in the result object, which will overwrite the default data. Now, we also require a copy constructor, and that uses the same trick to initialize the value or exception field depending on what we're copying from. Now, one of the most interesting features here is the destructor, so let's expand that. This uses a C++ feature that is even less well known than placement new. Since the fields in the union are not objects, we can't just call delete on them because that would attempt to free up their memory, which is actually part of the result. What we do instead is to run the destructor, but without freeing up the memory. Manually calling a destructor is something that many C++ developers think you can't do. But as you can see here, it's perfectly valid, even if not something you want to do unless you absolutely have to and really know what you're doing. The rest of the class is quite straightforward, with functions to check whether the object has a value and to return the value of the exception. Note that if someone tries to get the value when the operation has failed, rethrow exception will cause our exception pointer object to throw the actual exception it was holding. Now, the final function in the file returns the string associated with the underlying exception, and it might look a bit strange. It turns out that there isn't a way to get the actual exception directly out of the exception pointer. What you have to do instead is to use rethrow exception and then catch what it throws and process that. So let's see how this works. Here's another version of the parse function that this time returns a result object. If conversion works, then the return value is automatically converted to a result. If it doesn't work, then we use the fromException function to convert the exception object into a result. So when we try it, we can try converting valid and invalid strings, and the isValid function will tell us whether it's worked, and we can then get the value back, or we can get the string out of the exception or process it however we like, and we can show that working. So as a final exercise, revisit your implementation of chain of responsibility and see if you can find any places where you can use modern C++ features. While you're reviewing your code, think about how general your solution is and whether you can improve it. Can you think of any use cases that your implementation won't handle, and could you modify your implementation, or do you think you'd need another one? Sample implementation of this, as with the previous example, is available in the working files for this chapter.